Have you ever really thought about it? You tap a wine glass and you get that beautiful long ring, but then you knock on a wooden table and it's just a dull thud. It seems so simple, right? But the answer is actually pretty amazing. Today, we're going to pull back the curtain and look at the hidden physics behind every single sound you make. So yeah, this is really the heart of it all. On one hand, you've got the wine glass. You give it a little tap, and it just sings, doesn't it? A beautiful, clear ring. But then you do the exact same thing to a wooden table, and all you get is this flat, short thud. I mean, it's the same action, but the result is night and day. So, what's the deal? First, let's just think about that ting sound. It's sharp, it's clear, it's high-pitched. You get it from glass, from metal, and it kind of hangs in the air for a second, right? And then you have its total opposite, the thud. That flat, kind of lifeless sound you get from a book or a chunk of wood. The sound is there, and then, poof, it's gone in an instant. Understanding why that happens, well, that's where things get really interesting.
Okay, so to really get why those sounds are so different, we've got to trace the journey of sound from the very beginning. It's actually a super cool chain reaction that starts with that little tap and ends up right inside your ear. All right, let's zoom in, like way in, to see what's really going on. When you tap something, you're basically just giving it a little burst of energy. That energy makes the object itself start to wobble or vibrate really, really fast. And those vibrations push on the air around them, creating these invisible waves, sound waves. They travel through the air, hit your eardrum, and your brain goes, hey, I hear something. So really, all a tap is a way to get an object to start vibrating.
And that leads us to this, maybe the most important idea of all, something called natural frequency. You can think of it like an object's own unique voice, or its favorite note to sing. Every single thing, from a coffee mug to a skyscraper, has a specific speed it wants to vibrate at when you disturb it. And this, right here, is the secret sauce. It's the reason everything has its own distinct sound. So what does that frequency mean for us, for what we actually hear? Well, it's pretty simple. When something vibrates really fast, that's a high frequency, your brain hears a high-pitched sound. Think of a little bell. And when it vibrates slowly, a low frequency, you hear a low-pitched sound, like a giant drum. So there it is. The object's natural frequency is what decides its pitch, plain and simple. Okay, so if every object has this special acoustic fingerprint, this natural frequency, what creates it? What are the secret ingredients that give a glass its ting and wood its thud? Let's break them down. It really boils down to a recipe with 3 key ingredients. First up, what's it made of? We're talking about its material properties, specifically density and elasticity. Second, what does it look like? Its shape and size. And third, its structure. Is it hollow on the inside or is it solid all the way through? Okay, let's tackle the material first. Think about density. In something super dense, like metal, all the little atoms are packed together like sardines in a can. This means when you hit it, the vibration can travel through it super easily, like a wave moving through a tight crowd. It's really efficient. And that's why you get that clear, long-lasting ring. Now compare that to something like foam. The particles are all spread out, so the energy just gets soaked up and dies. The vibration is killed almost instantly. The other big material property is elasticity, and that's just a fancy word for how well something snaps back into shape after you hit it. Think about glass. It's super elastic. It wants to snap back to its original shape immediately, and that quick snapback lets it vibrate like crazy, creating that sharp ringing sound. But then you've got something like a lump of clay. You hit it, and it just kind of squishes, right? It doesn't snap back. It just absorbs the hit, killing the vibration. That's why you get that soft, muffled thump. So density and elasticity, they both feed into this magical thing called resonance. The best way to think about it is like pushing someone on a swing. You know how if you push at just the right moment in the arc, they go higher and higher with barely any effort? That's resonance. Objects are the same way. When they vibrate at their favorite frequencies, they're amazing at holding on to and amplifying that energy. It's like they're perfectly in sync with themselves. And that is why some sounds ring out so loud and clear while others just fizzle out. All right, let's talk about that third key factor, because this one's a game changer. I'm talking about whether something is hollow or solid. And trust me, the difference is like a whisper versus a full-on shout. So if you tap a solid block of wood, right, the vibrations just kind of travel through it and get absorbed pretty quickly. You get that classic thud. But if you tap something hollow, like the body of a guitar, something really cool happens. The wood vibrates, sure, but then it makes all the air trapped inside vibrate too. And that trapped air acts like a natural amplifier. It's like having a built-in speaker. This is what creates that rich, loud, beautiful tone. I mean, there's a reason guitars, violins, and drums are all hollow, right? Okay, let's put all the pieces together and look at the world around us. That wine glass, it rings because it's got the perfect combo. It's elastic, it has a nice uniform shape, and it's hollow. It's practically built to resonate. The wooden table, it thuds because it's solid wood and all those fibers just soak up the energy. And hey, this is actually how you find a stud in a wall. You knock, and if you hear a low, hollow boom, that's the sound of the air resonating between the studs. But when you hear that solid, high-pitched thud, bingo, you found the stud. All right, check this out. Here is a super simple little experiment you can do right now that puts all this stuff together. You've probably done it before without even thinking. You take a glass, you tap it, it rings. Then you add some water and tap it again. The pitch gets lower, right? But why? The answer is just beautiful, simple physics. By adding water, you're adding mass. You're making the whole system heavier. And just like it's harder to push a heavy swing than a light one, the glass now has more stuff to move, so it just can't vibrate as fast. And what did we learn? Slower vibrations mean a lower frequency, and a lower frequency means a lower pitch. It's that direct. You are literally changing the glass's natural frequency just by adding water. How cool is that? So once you get these basic ideas, frequency, what stuff is made of, and its shape, you really do start to hear the world differently. It's like every sound you hear is telling you a secret story about the object that created it. So what's the big takeaway from all this? It's that the ting, or the thud, you hear, it isn't just random noise. It's information. It's that acoustic fingerprint we talked about. And it's instantly telling your brain all about an object's density, how elastic it is, whether it's hollow or solid. And your brain processes all of that without you even having to think about it. It's incredible. So, the next time you're just tapping your fingers on a desk or you clink glasses with a friend, just pause for a second and remember what's really happening. You're not just making a sound. You are conducting a tiny, beautiful physics experiment. You're not just making noise, you're literally creating music from the laws of physics itself.